Let's look at divergence and curl. If F equals PQR is a 3D velocity vector field, then the divergence of F tells us the net rate at which fluid is flowing away from a point xyz. This is the tendency of a fluid to diverge from a point. That's why we call it divergence. Or if F represents heat flow, then the divergence of F equals the rate of heat loss. Here's the formula. If F equals PQR, then the divergence of F is partial P partial X plus partial Q partial Y plus partial R partial Z. Now this is a slick way to represent the formula. This equals del dot F if we think of del as a vector with components partial partial X, partial partial Y, partial partial Z. Why is that? Because then del dot F equals this. Again, that's del dot F. Okay, del dot F. When you look at the dot product of those two, it gives you partial P partial X plus partial Q partial Y plus partial R partial Z. So this is a slick way to remember the divergence of F, the formula for the divergence of F. For example, let F equal x cubed y cubed z cubed. Find the divergence of F at the point 1, 1, 0. Divergence of F is del dot F. In other words, partial P partial X, partial Q partial Y, plus partial R partial Z. That's going to be 3x squared, partial P partial X, plus 3y squared, partial Q partial Y, plus 3z squared, partial R partial Z. And this is what we get when we add those together. At the point 1, 1, 0, the divergence of F is going to be 3 times 1 squared, which is 1, plus 3 times 1 squared, which is 1, plus 3 times 0, because z equals 0. That's, in other words, 3 plus 3 plus 3 plus 3 plus 0, which is 6. So what does that mean? If at a point the divergence of F is greater than 0, the net flow is outward, and that point is called a source, because stuff is coming out of there. More heat or more fluid is flowing away from the point than flowing toward it. On the other hand, if at a point the divergence of F is less than 0, the net flow is inward, and that point is called a sink. It's like stuff going down a sink. More heat or more fluid is flowing toward the point than flowing away from it. Again, in the previous problem, we saw the divergence of F was 6. Since the divergence of F is greater than 0, the net flow is outward, and more is flowing away from the point than flowing toward it. This seems reasonable when we graph the vector field F equals x cubed, y cubed, z cubed using GeoGebra. Look at the point 1, 1, 0. So the point 1, 1, 0 is going to be over here. Okay, so that's roughly over here, roughly that point. Now notice, since it's x cubed, y cubed, z cubed, as we move further from the origin, the arrows grow longer, so the movement gets faster. I mean, x cubed, y cubed, z cubed grows pretty quickly as x and y and z increase. So the further we are from the origin, the bigger the arrows. These arrows, for example, further from the origin are pretty big. This arrow at 1, 1, 1 isn't very big at all. But as we move further from the origin, the arrows get much bigger. So in other words, stuff, whether we're looking at the flow of water or air or heat, is flowing or is entering 1, 1, 0 slowly and leaving 1, 1, 0 quickly. So more is flowing away from 1, 1, 0 than flowing into it. That's why the divergence of F is greater than 0. Here's another example. Let F equals 0, 0, y cubed plus y. Find the divergence of F. Again, it's just going to be partial P partial X plus partial Q partial Y plus partial R partial Z. In other words, the partial derivative of 0 with respect to x plus the partial derivative of 0 with respect to y plus the partial derivative of y cubed plus y with respect to z. Well, that's just 0 plus 0 plus 0, in other words, 0, and it's 0 everywhere. It doesn't matter what point we're looking at, it's going to be 0 everywhere. This seems reasonable when we graph the vector field F equals 0, 0, y cubed plus y. For a given value of y, the arrows are all the same. So all these arrows are all the same because corresponds to the same value of y. Looks like y equals 1. If we look at y equals negative 1, all of those arrows are going to be the same. At every point, the net rate is 0. The rate of flow towards the point equals the rate of flow away. So for example, at this point here, this arrow is the same as this arrow. The arrow going into the point is the same as the arrow going out of the point. They're identical. So the net rate is 0. Stuff flowing in equals stuff flowing out. If the divergence of a vector field is 0 everywhere, as it is in this case, the vector field is source-free. Doesn't have a source, doesn't have a sink. Let's talk about curl. If F equals PQR is a 3D velocity vector field, then the curl of F tells us the axis about which a fluid is flowing. A tiny paddle wheel would turn most quickly if its axis lay along this line. So here's an example of a paddle wheel. If you have water flowing, it's going to make this paddle wheel turn. So it's going to turn like that, turn clockwise if the water is flowing like that. The question is, how should you turn the paddle wheel so as to make it turn most rapidly? Well, whatever axis makes the paddle wheel turn most quickly, here's the axis of the paddle wheel, that's going to be the curl of the vector field. Or in this case, the vector field here would be the flow of water. Here's the definition of curl. It's a determinant. It's a cross product, really. IJK, partial x, partial y, partial z, PQR. This is a handy way to represent it. It's just del cross F. If, again, we think of del as a vector with components partial x, partial y, partial z. Because then this is del, and this is F. And so we're just calculating del cross F. Really, this is a slick way to remember how we define the curl of F. Let's look at this example. F equals 0, 0, y cubed plus y. That's the same vector field we saw a moment ago. Find the curl of F at the point 1, 0, 0. The curl of F, again, is going to be del cross F. Del is partial x, partial y, partial z. And this is F, 0, 0, y cubed plus y. We know how to calculate a cross product. It's this determinant. So it's going to be I times this determinant, which is the partial derivative of y cubed plus y with respect to y. So it's this, minus the partial derivative of 0 with respect to z times I. And then the minus j times this partial derivative of y cubed plus y with respect to x, minus the partial derivative of 0 with respect to z, plus k times this determinant. Partial derivative of 0 with respect to x minus the partial derivative of 0 with respect to y times k. So we end up with 3y squared plus 1 minus 0 times I minus 0 times j plus 0 times k. That simplifies to 3y squared plus 1i minus 0j plus 0k. So at the point 1, 0, 0, the curl of F is 3 times 0 squared plus 1, 0, 0. In other words, it's 1, 0, 0. That's the curl of F. This seems reasonable when we graph the vector field F equals 0, 0, y cubed plus y using GeoGebra. Look at the point 1, 0, 0. So again, the point 1, 0, 0 is right over here. Okay? If we want the paddle wheel to spin most rapidly, then the axis of the paddle wheel should be parallel to 1, 0, 0. So yeah, it's just gonna look like this. So the axis is gonna be parallel to the x-axis, 1, 0, 0. And here's why, because then your paddle wheel is gonna look like this. And then notice these water currents or air currents or whatever kind of current they are. These are going up and these are going down. And so that's going to cause your paddle wheel to spin counterclockwise like that. And if you want it to spin most rapidly, it does seem like you'd want to position it like this, so that the axis of the paddle wheel is parallel to the x-axis. Let's look at another example. Let f equal x, negative y, x, y, z. Find the curl of f at the point 1, 2, 3. Curl of f, del cross f, is going to look like this. Let's calculate this determinant. So it's going to be I times this determinant, the partial derivative with respect to y of x, y, z, minus the partial derivative of negative y with respect to z times I, minus the partial derivative of j, Okay, so yeah, minus j times this, this determinant. So it's the partial derivative of xyz with respect to x minus the partial derivative of x with respect to z, that's times j. And the partial derivative, okay, and then k is going to be this determinant. So the partial derivative of negative y with respect to x minus the partial derivative of x with respect to y. So this minus this. And that's times k. Okay, so when we simplify all of that, here's what we get. Partial derivative xyz with respect to y, that's xz. Partial derivative negative y with respect to z, that's 0. Partial derivative of xyz with respect to x is yz. Partial derivative of x with respect to z, that's 0. And then these partial derivatives are just 0. So we end up with xz minus yz plus 0k. So at the point 1, 2, 3, the curl of f equals xyz xzi minus yzj plus 0k. In other words, when we plug in 1, 2, and 3 for x, y, and z, we get 1 times 3i minus 2 times 3j plus 0k. In other words, we get 3, 6, 0. Let f equal pqr be a vector field defined on all of R of 3, or at the very least on a simply connected domain. Suppose f has continuous partial derivatives. The curl of f equals 0 if and only if f is conservative. So this is one way to determine if a three-dimensional vector field is conservative. Evaluate its curl. If the curl of f is indeed 0, we say that f is irrotational. It has no whirlpools or eddies. This is one characteristic of what we call an ideal fluid. For example, if water is flowing through a pipe and all the water is flowing at the same rate, then f is irrotational. I've tried to illustrate that here. So imagine this represents water flowing through a pipe. This would be an example of an irrotational vector field, because it's not that you've got this little whirlpool here. You haven't got stuff like that. So now we have learned about grad, div, and curl. Grad f, we call it the gradient div f. That's del f. That's partial f, partial x, partial f, partial y. In other words, f sub x, f sub y. Or if we're talking about 3 dimensions, it's going to be f sub x, f sub y, f sub z. Div f is del dot f. Curl f is del cross f. By the way, fun fact, the divergence of the curl of f is 0. So where on earth are you going to use all of these things? It turns out that Maxwell's equations, named after the great physicist James Clerk Maxwell, these are based on divergence and curl. Okay, notice del dot E, it's going to be rho over epsilon 0. And these other ones are also based. Are going to be based on divergence and curl. This is where E is the electric field, rho is the electric charge density, epsilon sub 0 is the vacuum permittivity, B is the magnetic field, mu sub 0 is the vacuum permeability, and J is the current density. So these foundational formulas for electromagnetism are based on divergence and curl. And that's where you're going to see them. That's one place you're going to see them.